linear harmonic oscillator. There are two types of linear harmonic oscillator. One is symmetric and other one is asymmetric. And 1D LHO is there, 2D LHO is there, and 3D LHO is there. So 1D LHO also can have a symmetric and unsymmetric, and a 2D LHO also can have a symmetric and asymmetric, and so on. Okay. Earlier, when we are discussing the box problem, particularly in a box problem, we discussed 1D case, 1D box, 2D box, and a 3D box, and we discussed symmetric case and the asymmetric case. Okay, in a similar fashion, in linear harmonic oscillator also, we will discuss all these ideas. So first, I will discuss this 1D linear harmonic oscillator in classical mechanics. So you will get a real idea about the oscillator. Then we will extend these ideas to quantum mechanics. Then we will discuss about wave function of 1D LHO and energy of 1D LHO, and then expectation value of particle in different states, and the ladder operators. Then we extend this idea of 1D LHO to 2D and 3D. Okay. And we consider these two cases, symmetric and asymmetric also. Okay. This is the overview of lectures on linear harmonic oscillator. Okay. So first I am going to start with 1D LHO in classical mechanics. So we are starting with the 1D linear harmonic oscillator, and first we discuss this 1D linear harmonic oscillator in classical mechanics. So this is a harmonic oscillator in classical mechanics. There is a spring and a mass m is attached to it, and it is oscillating about a mean position. Okay, so there is a spring constant k, so there is a force law that is equal to minus kx. And in the classical mechanics, we know the force is nothing but negative gradient of potential, that is minus dv by dx. So I can find out the potential energy of a linear harmonic oscillator by integrating this function, that is v is equal to minus integral f dx. That is, I can substitute this value of f, that is minus integral f is minus kx dx, that is equal to v is equal to kx square by 2, that is 1 by 2 kx square. So this is the potential of a 1D harmonic oscillator. V is equal to half kx square. If you have plot this in a x and y coordinate, that is x is x and the y coordinate is v of x, then this function v will look like this. Okay, this is the potential function corresponds to v is equal to half kx square. Now I want to find out this k value. What is this k value and how we can find out the k value? So I am going to use Taylor series expansion. That is, if there is a function f of x, then we can expand this function at some point x equal to a. Then the expansion will be f of x is equal to f of a plus 1 by 1 factorial into x minus a raised to 1 f dash of a plus 1 by 2 factorial into x minus a whole square f double dash of a plus etc etc. So here I am going to expand this potential function, that is v of x at x equal to a. That is v of x is equal to v of a plus 1 by 1 factorial x minus a into f dash of a. That is, I have to take the derivative of this v of x, that is equal to dou by dou x of v of x at x equal to a plus 1 by 2 factorial x minus a all square into dou square by dou x square of v of x at x equal to a plus etc. And if this x equal to a is equilibrium point, then we know from stability analysis, then at that point the derivative dou v of x by dou x will be equal to 0. That is, slope will be equal to 0 at equilibrium point. The equilibrium point may be stable equilibrium or unstable equilibrium, but for an equilibrium point, the slope must be equal to 0. Therefore, this term is equal to 0. Therefore, the expression for v of x reduces to v of a plus 1 by 2 factorial x minus a whole square dou square v of x by dou x square plus all other terms will be equal to 0. And here you can see, when you are taking dou square v by dou x square, you will get a value, that is k. That is, v of x minus v of a is equal to 1 by 2 x minus a all square into k, that is k into x minus a all square. And here the k value is equal to dou square v by dou x square at x equal to a. From this equation we can find out the omega value, that is omega is equal to root 1 by m into dou square v by dou x square. Actually, all these ideas we already discussed in classical mechanics itself when we are discussing the stability analysis problems. Okay. Earlier I told you about two potentials. One is v of x equal to half k x square, and this potential function will look like this one. That is, this is x equal to 0, and the v of x will look like this one. Okay, and I told you another function, that is v of x minus v of a is equal to 1 by 2 k into x minus a whole square. So this potential function will look like this one. This is x equal to a, and this will be the v of x. Okay, that means the origin is at the x equal to. Example problem. The question is to find out the frequency of oscillation. There is a potential is given, and find out the frequency of oscillation. To find out frequency of oscillation, we have the equation, that is omega equal to root k by m. What is k? K is equal to dou square v by dou x square. That is, this is equal to root 1 by m into dou square v by dou x square. Okay, that is the expression. So the first question, v of x is equal to minus a x square plus b x raised to 4. So how we can solve this? To solve this, first we have to find out equilibrium point. Right. And how we can find out equilibrium point? That is, at equilibrium point, slope is equal to 0. That means dou v of x by dou x is equal to 0. And This equilibrium point may be two type. One is stable and other is unstable. If it is an unstable equilibrium, then there will not be any omega. Only stable equilibrium have a frequency of oscillation. So next you have to find out the type of equilibrium point. So how we can find out? If it is a stable equilibrium point, then dou square v by dou x square will have a positive value. And if it is a negative value, then it is a unstable equilibrium point. So if it is a stable equilibrium point, then we can calculate omega is equal to root 1 by m dou square v by dou x square. So we will get the frequency of oscillation. If it is unstable, then we cannot say frequency of oscillation, because about an unstable equilibrium point, the particle can oscillate. So there will not be any frequency. So the first step is we have to evaluate slope of this function, that is dou v of x by dou x. That is equal to minus 2ax plus 4bx cube. And we have to equate this value to 0. So we can take x outside. So minus 2a plus 4bx square is equal to 0. So x may be equal to 0 or minus 2a plus 4bx square equal to 0. Here one of the values x equal to 0 and other one is 4b x square is equal to 2a. Therefore x square is equal to 2a by 4b, that is x equal to root a by 2b. Okay, so these are the two equilibrium points. One is x equal to 0 and other is x equal to root a by 2b. That is plus or minus root a by 2b, right? Now we have to evaluate. The second step is evaluate the stability. That is, we have to check whether it is a stable equilibrium point. If it is a stable equilibrium point, then dou square v by dou x square will be greater than 0. So we have to take second derivative of potential, that is dou by dou x of dou v by dou x. That is, dou v by dou x is already derived. That is minus 2ax plus 4bx cube. That is equal to minus 2a plus 4 into 3, that is 12bx square. Now we have to check which equilibrium point is satisfying this condition. That is, we have to substitute x equal to 0 and x equal to plus or minus root a by 2b. If x equal to 0 is positive, then we can say x is the stable equilibrium point, and if x equal to plus or minus root a by 2ab is positive, then we can say this one is the stable equilibrium point. That is dou square v by dou x square at x. So first we are taking x equal to 0, that is minus 2a plus 12b into 0. So see, this one is a negative value. So this is unstable equilibrium point. Now we have to check dou square v by dou x square at x equal to plus or minus root a by 2b. That is minus 2a plus 12b into x square, that is a by 2b. So definitely this value is positive, right? So this is the stable equilibrium point. So the frequency of oscillation omega will be equal to root 1 by m dou square v by dou x square at stable equilibrium point, that is x equal to plus or minus root a by 2b. So here we can find out the value. So this is equal to minus 2a plus, we can cancel this b and b. So 6 that is 4a. So we can substitute this value in this equation, that is root 1 by m into dou square v by dou x square at x equal to plus or minus root a by 2b is 4a. That is root a by m. 2 into root a by m. This is the frequency of oscillation. Second example problem, that is v of x is equal to a by x square minus b by x. So the first step is we have to find out dou v by dou x equal to 0. That is, at equilibrium point, the slope will be equal to 0. So by using this expression, we can find out the equilibrium points of this potential. That is dou by dou x of a into x raised to minus 2 minus b x raised to minus 1. That is equal to minus 2ax minus 3 minus plus b x raised to minus 2. And we have to equate this value to 0. Therefore, we get minus 2a by x cube is equal to minus b by x square. So we can cancel this minus, and we can cancel this x square and this x square. Okay, so we will get x is equal to 2a by b. So this is the equilibrium point. Now we have to find out whether this equilibrium point is stable or unstable. For only stable equilibrium, it will have a frequency of oscillation. So the condition is dou square v by dou x square should be greater than 0 for the stable equilibrium point at the equilibrium point. Okay. So here, what is the equilibrium point? That is x equal to 2a by b, right? Now we have to evaluate the second derivative of potential. That is dou by dou x of, we know the first derivative of potential is this one, right? That is minus 2a x raised to minus 3 plus b x raised to minus 2. That is equal to minus 2 into minus 3 into a raised to x raised to minus 4 minus 2b x raised to minus 3. That is equal to 6a x raised to minus 4 minus 2b x raised to minus 3. Now we have to substitute our equilibrium point value, that is 2a by b, x equal to 2a by b. For simplification, I am rewriting this expression, that is 6a by x raised to 4 minus 2b by x cube. That is, now I can substitute this value, x equal to 2a by b, that is 6a by 2a by b all raised to 4 minus 2b by 2a by b all cube. So we can rearrange, that is 6a by 2a raised to 4 into b raised to 4 minus 2b by 2a cube into b cube. That is, this is equal to 6a b raised to 4 by 2 raised to 4, that is 16a raised to 4 minus 2b raised to 4 by 2a raised to 3, that is 8a cube. Here we can cancel some values, this a and a raised to 4 we can cancel, that is 6b raised to 4 by 16a cube minus 2b raised to 4 by 8a cube. So we can multiply this equation by 2 and divide by 2. So it will be 6b raised to 4 by 16a cube minus 4b raised to 4 by 16a cube. So we can easily find out the solution, that is 6 minus 4, that is 2b raised to 4 by 16 a cube, that is equal to b raised to 4 by 8 a cube, right? So this is our dou square v by dou x square at equilibrium point. So here the question is to find out the frequency of oscillation. Therefore, we have to use the expression, that is root 1 by m into dou square v by dou x square at a equilibrium point, stable equilibrium point. That is omega is equal to root 1 by m into, we got the value of dou square v by dou x square at equilibrium point, that is equal to b raised to 4 by 8 a cube. So this is the answer. Another example problem, that is v of x is equal to a x square plus b by x square. So the first step is we have to find dou v of x by dou x, and we have to equate this value to 0. That is dou by dou x of a x square plus b x raised to minus 2 should be equal to 0. So we can find out the equilibrium points. That is 2ax minus 2bx raised to minus 3 equal to 0. That is 2ax equal to 2bx raised to minus 3. So we can cancel this 2 and 2. So, and we can rearrange this x value. So x raised to 4 is equal to b by a. So this is the equilibrium point. Now the second step is we have to evaluate dou square v by dou x square, and if it is greater than 0, then it will be a stable equilibrium point. That is, when we are substituting this value, x raised to 4 is equal to b by a, and if we got it is greater than 0, then we can say it is a stable equilibrium point. And if it is a stable equilibrium point, then there will be omega. Otherwise, there will not be any omega. So now we have to evaluate dou square v by dou x square, that is dou by dou x of dou v by dou x, that is 2ax minus 2b x raised to minus 3. That is equal to 2a minus 2 into minus 3, that is plus 6b x raised to minus 4. Now we have to substitute this equilibrium point, that is dou square v by dou x square at x equal to b by a, x raised to 4 equal to b by a. So we have to substitute this value, x raised to 4 is equal to b by a. So we will get 2a plus 6b into a by b. So b will cancels. So we get 2a plus 6a, that is 8a. So we can find out the omega, that is root 1 by m into 8a. Now I am going to discuss about one-dimensional linear harmonic oscillator in quantum mechanics. That is, in classical mechanics, we've seen that the potential of a linear harmonic oscillator is half k x square. And in quantum mechanics, I want to find out two things. One is wave function. You know, the particle in quantum mechanics is represented by a wave function, and I want to find out the energy of the particle. So it can have different type of wave function. So different type of wave function will have different energies. So I want to find out these two equations. How we can find out the wave function? By solving the Schrodinger equation. What is Schrodinger equation? Schrodinger equation is del square psi plus 2m by h cross square e minus v psi equal to 0. Here, in this case, the potential is half k x square. So we have to substitute this v is equal to half kx square and solve this Schrodinger equation. So finally, we will get a solution, and that solution will be sine of x equal to a e raised to minus half alpha square x square hn of alpha x. Here I am not going to do the derivation because it is a lengthier one and it is not necessary, and you already done those derivation in your PG class. Here we need only the final expressions and the physics. So here you see this function is a Gaussian function. Earlier I told you if a function is in the form of minus some constant a into x square, okay, then such kind of functions are called the Gaussian function. And what is this hn of alpha x? This is Hermite polynomial. So this is the wave function corresponds to a particle in 1D linear harmonic oscillator. And here I tell you what is the value of alpha square. This alpha square is equal to m omega by h cross. And maybe you have a doubt, what is this Hermite polynomial? And there is n values there, and for different n values 0, 1, 2, 3, etc., we have to find out the Hermite polynomial. That is the hn values corresponds to different wave functions. Okay, so how we can find out the Hermite polynomial? To generate Hermite polynomial, we can use Rodriguez formula. What is this Rodriguez formula? If you know this Rodriguez formula, then you can find out any hn value. So the formula is hn of x is equal to minus 1 raised to n e raised to x square d raised to n by dx raised to n e raised to minus x square. So by substituting n equal to 0, you can find out h0 of x, and 1 you can find out h1 of x, and etc. So I'm going to solve some of these values. That is, first I'm taking n equal to 0. Then what will be the h0 of x? That is, you have to substitute n equal to 0 in all the terms. That is minus 1 raised to 0. That is 1, right? And here derivative d raised to 0. That is, there is no derivative. So what we get? That is minus 1 raised to 0 into e raised to x square into, there is no derivative because d raised to 0. Okay, into e raised to minus x square. So these two terms will cancel each other, and this is equal to 1, right? And this value is also equal to 1. So we will get this is equal to 1. Now what is n equal to 1? That is h1 of x, that is equal to minus 1 raised to 1 e raised to x square d by dx into e raised to minus x square. So this is equal to minus 1 into e raised to x square into derivative of e raised to minus x square is e raised to minus x square into minus 2x. That is equal to minus and minus will cancels, and you get 2x. And if you solve for other values, that is n equal to 2, you will get h2 of x is equal to 4x square minus 2. And if you substitute n equal to 3, you will get h3 of x, that is equal to 8x cube minus 12x. So please remember all these values. Okay, and we can find out the energy of the particle in 1D linear harmonic oscillator, and we will obtain this energy En equal to n plus half h cross omega. Let us summarize all these ideas. That is for a one-dimensional linear harmonic oscillator in quantum mechanics, the wave function is equal to a e raised to minus half alpha square x square into hn of alpha x, where alpha square is equal to m omega by h cross and various values of hn of alpha x, that is h0 is equal to 1, h1 is equal to 2 alpha x, and the h2 is equal to 4 alpha square x square minus 2, and the h3 of alpha x is equal to 8 alpha cube x cube minus 12 alpha x. Okay, and the energy expression En is equal to n plus half h cross omega. So please remember these values. Ladder operator method. What is this ladder? You know, ladder. This is a ladder, right? So it will have different steps, and if you are climbing through a ladder, you can stand this position. Okay, then you can stand this position, then you can stand this position. Okay, and you are unable to stand in between these two steps. Okay, so if you want to go higher, you have to jump to the next step. There is no way to stand in between these two steps. Okay, that is, this is not continuous, this is discrete. Here we seen that the wave function psi n is equal to, for 1D LHO, okay, we are discussing for 1D LHO, psi n is equal to a e raised to minus half alpha square x square hn of alpha x. See, this n can have values 0, 1, 2, 3, etc. That is, it is discrete values. It can have a value in between 0 and 1 and a value in between 1 and 2, similar to a ladder. And energy also, n is equal to n plus half h cross omega. That is, n is equal to 0, 1, 2, 3, etc. only. There is no half value, or there is no 1.5 value, etc. Okay. That means it is like climbing a ladder. If you are in the ground state, then your n value will be equal to 0 and you will have a energy. Okay, that is half h cross omega. Then you can jump to another state, that is n equal to 1. And in that state, you have an energy, that is 3 by 2 h cross omega. Okay, in between this 3 by 2 h cross omega and half h cross omega, there is no energy level is possible. That is why we can use ladder operators in quantum mechanics, because these values are discrete, not continuous. You know, everything in quantum mechanics is quantized, right? Therefore, we can use ladder operators to solve some problems. Okay, we will discuss the kind of problem we can solve using ladder operators. Creation and the annihilation operator. The creation operator is represented as a cap dagger, and annihilation operator is represented as a cap. What is this creation and annihilation operator? Actually, these are a combination of a Hermitian and a anti-Hermitian operator, that is x cap and I p x cap. We know Hermitian operator. We know x cap is a Hermitian operator. And we know px cap is also Hermitian operator, but ipx cap is a anti-Hermitian operator. So the combination of Hermitian and anti-Hermitian operator is called one of the combination is called the creation operator and other is called the annihilation operator. So if you are going to combine x and the I p x cap, then we will obtain creation operator a dagger, and if we add, and we will obtain annihilation operator if x cap plus ip x cap. This is not the exact form, but this is the idea. The exact expression is a dagger creation operator is equal to 1 by root 2m h cross omega into m omega x cap minus I p x cap. An annihilation operator is equal to 1 by root 2m h cross omega into m omega x cap plus I p x cap. And what this creation and annihilation operator will do? That is, if creation operator is there, and if this creation operator operates on certain state n, then we will get a eigenvalue and the state become n plus 1. State is increased, right? That is, it is created the higher state. And if annihilation operator is operating on certain state, that is a cap operating on n, then what will happen? We will get an eigenvalue and the n value will be reduced to n minus 1. That is, one state is annihilated to its lower energy state. So if we draw a diagram, you will get more clear idea. That is, this is our linear harmonic oscillator potential. So there will be different energy level. This is potential V of x. Okay, so the particle can have in different wave functions. So each wave function is corresponds to different energy levels. And we know the energy expression is En equal to n plus half h cross omega. And this n can have values 0, 1, 2, 3, etc. Okay, and this each En values corresponds to each psi n value. So this is the one of the wave function and its corresponding energy E is equal to half h cross omega, that is n equal to 0. And next one is n equal to 1. So the corresponding energy will be E is equal to 3 by 2 h cross omega, and next step is n equal to 2, that is energy E is equal to 5 by 2 h cross omega, and so on. If it is n equal to 3, then this is E is equal to 7 by 2 h cross omega. Okay, so suppose our particle is in this state, that is n equal to 2 state, and the creation operator is operating on that state, then what will happen? The particle will jump to higher energy state. That is, see, here is n. Now the n become n plus 1. Okay, and if the particle is in this state and an annihilation operator is operating on it, then what happen? See, E operating on n, the state is reduced by 1. So it will come down to the lower state. That is how we can jump to higher state, by absorbing some photon h cross omega, and how it can jump to lower state by emitting some energy h cross omega in the form of photon, right? So you can see the difference between different energy level is h cross omega. So this is the idea of creation and the annihilation operator. Here I told you when creation operator will operate on a state, we will get a eigenvalue. But we don't know what is the eigenvalue. So we have to find out the eigenvalue we obtain after operating a creation operator, and here also we have to find out this eigenvalue. When an annihilation operating on a certain state, then what will be the lambda? So we have to find out this lambda values of creation and the annihilation operator. That is our next step. So I am considering our creation operator first. So when this creation operator operates on a state, then we will obtain an eigenvalue and the state become n plus 1. Now I am going to take its complex conjugate. So what we will get? We will get bra n a dagger become a, right, is equal to bra n plus 1 lambda. When we are taking the complex conjugate of this value, that is lambda star. Now what I am going to do is, I am going to multiply this term by this one, that is bra n. Annihilation operator. Next one is creation operator. Get n is equal to bra n plus 1 lambda star into lambda get n plus 1. Here this is a constant value, so we can take it outside, that is equal to lambda star into lambda. Here it is lambda square only, right, into n plus 1, n plus 1. And we know scalar product of same state is equal to 1. That is bra n a dagger get n is equal to lambda square. And here this a dagger value is equal to h by h cross omega plus half. Don't worry, we will derive this value. Okay, so now we can substitute this value here, that is bra n h by h cross omega plus half get n is equal to lambda square. So this is Hamiltonian operator. So I can expand this function, that is bra n h cap by h cross omega get n plus bra n 1 by 2 get n equal to lambda square. Again, here this h cross omega is a constant term, so I can take it outside into bra n h cap n plus, here 1 by 2 is a constant term, so I can take it outside, bra n get n is equal to lambda square. See, this one is nothing but equal to 1, and this one is expectation value of Hamiltonian operator, that is nothing but energy En, that is equal to n plus half h cross omega. This is the energy of 1D harmonic oscillator, linear harmonic oscillator, right? So we can substitute this value in this expression, that is 1 by h cross omega bra n plus half into h cross omega into get n plus 1 by 2 is equal to lambda square. Here also this one is nothing but a constant term, so we can take it outside, that is 1 by h cross omega into n plus half into h cross omega into bra n get n plus half equal to lambda square. Here also this one is nothing but is equal to 1, and here we can cancel this h cross omega and h cross omega, so that is equal to n plus 1 is equal to lambda square. Therefore we got lambda is equal to root n plus 1. That is, the initial expression is a dagger get n is equal to lambda into get n plus 1, right? So now we can substitute this value of lambda. So we will obtain a dagger get n is equal to lambda is root n plus 1 get n plus 1. This is the expression for creation operator. When a creation operator operates on certain state n, then we will get an eigenvalue, that is root n plus 1, and we will get a higher energy state, that is n plus 1. Okay, that is state is increased by 1. That is why I told you these are ladder operators. So you can jump by 1. So one step to another step, right? And there is no states in between these two steps. Next one is annihilation operator. That is a cap. And we know if an annihilation operator operates on certain state, you will get an eigenvalue and state will be reduced by 1. Here also I am going to take its complex conjugate. That is bra n a dagger is equal to bra n minus 1 lambda star. Now I am going to multiply this term by this one. That is bra n a dagger a get n is equal to bra n minus 1 lambda star lambda get n minus 1. Here this one a dagger a is equal to h by h cross omega minus half. Don't worry, we will derive these values later. So we can substitute this value here, that is bra n h by h cross omega minus 1 by 2 get n equal to bra n minus 1 lambda star lambda is lambda square get n minus 1. Here this one is a constant value, so we can take it outside. So product of these two terms is equal to 1. That is, and we can expand this function, that is 1 by h cross omega bra n h n minus 1 by 2 bra n get n is equal to lambda square. And here this is nothing but expectation value of h, that is h is Hamiltonian, that is expectation value of h is energy. And we know energy of 1D LHO, that is n plus half h cross omega. And n can have values 0, 1, 2, etc. Right? So we can substitute this value of Hamiltonian here, that is 1 by h cross omega and bra n, h values n plus half into h cross omega get n minus 1 by 2. See, this one is equal to 1 equal to lambda square. Similarly, we can take this is a constant value, so we can take its outside. So the product of bra n and get n become 1. That is, we get 1 by h cross omega into n plus half h cross omega minus 1 by 2 is equal to lambda square. That is, we can cancel these values, and here n plus half minus half, so we will get n is equal to lambda square. That is, lambda is equal to root n. Now we can substitute this value of lambda in the earlier expression. That is, what is the earlier expression? Annihilation operator operating on n is equal to lambda n minus 1. That is, we will get a operates on n is equal to what we got lambda, that is root n get n minus 1. So when an annihilation operating on a state, then its value will be reduced by 1 and the eigenvalue will be root n. Okay. So let us summarize. We got a creation operator a dagger is equal to 1 by root 2m h cross omega into m omega x cap minus I px. See, Here there is a dagger, that is plus sign. So if there is a plus sign, then this will be negative, right? And for annihilation operator, this is creation, right? Creation have this dagger and annihilation don't have dagger. That is equal to 1 by root 2m h cross omega into m omega x cap plus I p x cap. If there is no dagger, that is plus sign, then here it will be plus. Okay, and we got a dagger. If operates on certain state n, we will get root n plus 1 get n plus 1. And if annihilation operator operates on certain state, we will get root n get n minus 1. Okay, please remember these two equations. So very important. So we know the creation operator a dagger is equal to 1 by root 2m h cross omega into m omega x cap. See, this is dagger, right? Plus sign. So it becomes minus I p x. Okay, and we know the annihilation operator, that is a is equal to 1 by root 2m h cross omega m omega x cap plus I px cap. Okay, now we are going to find out some combinations of creation and annihilation operator. First one is a cap, a dagger. Second one is a dagger a, and the third one is commutator a dagger, and some other combinations also. So first I'm going to discuss about this one, that is a dagger. That is a dagger is equal to these two times, right? First we have to take this one, then this one. That is we get 1 by 2m h cross omega into m omega x cap plus I p x cap into a dagger, that is m omega x cap minus I p x cap. Now we can multiply these terms, that is equal to 1 by 2m h cross omega into m square omega square x square minus I m omega x cap p x cap plus I m omega p x cap x cap. Here the order of this operator is very important because all are operators. Okay, and minus I into minus I, that is plus p x cap square. Here I can rewrite this term as I omega p x cap commutator p x cap x cap. Okay, that is we got a dagger is equal to 1 by 2m h cross omega into m square omega square x square plus px square plus I omega. Sorry, I missed one m term also here. That is I m omega p x cap x cap. Here I can rewrite this expression as a dagger is equal to, I'm taking 1 by h cross outside and I'm taking this 1 by 2m inside, that is I will get m square omega square x square by 2m plus px square by 2m, and I'm taking 1 by 2m into h cross omega here. Remaining term is plus I m omega p x cap divided by 2m h cross omega. So here we can cancel this m square and one of the m, and we can rewrite this expression, that is a dagger is equal to 1 by h cross omega into px square by 2m plus 1 by 2 m omega square x square plus, here what is this px x cap? It is nothing but minus ih cross. Why minus? Because the order is interchanged. Okay, and here we can multiply this I into minus I, so it will be plus 1, right? That is and we can cancel this h cross m and the omega time, so the remaining time is only 1 by 2. And here what is this time? This is nothing but Hamiltonian operator, that is, this is corresponds to kinetic energy and this time is corresponds to the potential energy, right? That is, we got a dagger is equal to h cap by h cross omega plus 1 by 2. Now we want to evaluate the second one, that is a dagger A. So what is this a dagger A? A dagger A is equal to 1 by 2m h cross omega into m omega x cap minus I px into m omega x cap plus I px cap. That is, a dagger A is equal to 1 by 2m h cross omega into, we can multiply these terms, that is m square omega square x cap square plus I m omega x cap px cap minus I m omega px cap x cap plus px cap square. Here we can write this term as I m omega commutator x cap px cap, that is I m omega into x cap px cap is I h cross, right? That is equal to I into I minus, that is minus m omega h cross. That is the value of this entire term. So we got a dagger A is equal to 1 by 2m h cross omega into m square omega square x cap square plus p x cap square minus m omega h cross. Now, as we done earlier, we can multiply this 1 by 2m inside, that is 1 by h cross omega into m square omega square x cap square by 2m plus px cap square by 2m minus m omega h cross by 2m h cross omega. So we can cancel these terms, right? And here we can cancel this m and this m, and finally we will get a is equal to 1 by h cross omega into p x cap square by 2m plus 1 by 2m omega square x cap square minus 1 by 2. Sorry, here. Okay, bracket is here. Here what is this value? This is nothing but Hamiltonian operator, that is a dagger A is equal to h cap by h cross omega minus 1 by 2. So we got a dagger is equal to h by h cross omega plus half, and we got a dagger A is equal to h by h cross omega minus half, right? Now we want to evaluate commutator a dagger. That is, we can expand this commutator, that is a dagger minus a dagger A. That is, what is A dagger? H by H cross omega plus 1 by 2 minus A dagger is H by H cross omega minus 1 by 2. So what we get? See, this term will cancels and we get 1 by 2 plus 1 by 2, that is commutator A dagger is equal to 1. Now let us summarize. First one is A dagger is equal to H cap by H cross omega plus 1 by 2. Second one is A dagger A is equal to H cap by H cross omega minus 1 by 2. And third one is commutator A dagger is equal to 1. So please remember these three equations. If you know these three equations, then you can solve many problems relating commutator and the creation and annihilation operators. Example problem. First one, commutator A comma A dagger. What is the value? See, we can write this as commutator A comma A dagger plus commutator A comma A dagger A. We already learned how to expand this commutator, right? So here we know commutator with the same term will be definitely equal to 0. And we know the commutator of A dagger, what is it? That is equal to 1, right? So we got the answer equal to A. Another one, commutator A dagger comma A dagger. Here also we can expand this commutator operator, that is A dagger A dagger, right? So first I take combination of these two and I took this one outside. Okay, plus now I have to make combination with these two, right? That is A dagger and the remaining term is A, so that I take here. Why? Because in the first case the remaining term is on the right hand side of commutator, right? And we taking the next combination, the remaining term should be on the left side of commutator operator. Here it is right side of commutator operator, right? So that you have to follow because these are operator, therefore the position of operator are very crucial. Okay, here you know these are two same operators, so definitely its commutator value is equal to 0 and this is equal to, here we can rewrite this commutator, that is minus A dagger. This also we discussed when we are discussing the property of commutator operator. Okay, into A dagger. Therefore we know this value, what is this? This is equal to 1. Therefore we get this is equal to minus A dagger. Third example problem, commutator A H. How to find out? Here, if you know the Hamiltonian in terms of A and A dagger, then it is very easy to solve. So, okay, so is any way to find Hamiltonian in terms of A and A dagger? Yeah, yes. We know A dagger is equal to H by H cross omega plus 1 by 2. Or we know A dagger A is equal to H by H cross omega minus half. So we can use any of this equation. So from this equation we can find out H in terms of A and A dagger. In this equation also we can find out H in terms of A and A dagger. That is, here H by H cross omega is equal to A dagger minus half. Therefore we can find out H, that is equal to H cross omega into A dagger minus half. And from this equation, H by H cross omega is equal to A dagger A plus 1 by 2. Therefore, H is equal to H cross omega into A dagger A plus 1 by 2. Where this A dagger A is called the number operator, that is n is defined as A dagger A. Okay, so by using this expression for H, we can find out commutator AH. Suppose I am using this first equation, that is AH is equal to A into H cross omega A dagger minus half. That is equal to, I can expand this commutator, that is A comma H cross omega A dagger minus H cross omega by 2. That is equal to A H cross omega A dagger minus A H cross omega by 2. Okay, here this is operator and this is constant value. And I told you, commutator of an operator with the constant is equal to 0. Okay, and here I can take this H cross omega outside because it is a constant value. That is equal to H cross omega commutator A comma A dagger. Actually, we already solved this value, right? Okay, no problem. We can do it again. That is H cross omega into commutator A comma A dagger plus commutator A comma A dagger A. Okay, see, this is same operator, so it will be equal to 0, and for this one we know the value is equal to 1. Therefore, we will get AH is equal to H cross omega A. Okay. Similarly, please find out the answer using this Hamiltonian. So this is a work for you. Find the answer, that is AH. And one more work for you, that is fourth one, that is commutator A dagger H. Find out the answer. I tell you the answer will be minus H cross omega A dagger, but please solve and reach to the answer. Okay. Here we are discussing about linear harmonic oscillator and one dimensional case. Okay, now we want to find out the expectation values. So we know the creation operator, that is A dagger, and we know annihilation operator, that is A. Now I want to find out expectation value of A dagger and the expectation value of A and expectation value of combination of these two, that is A plus or minus A dagger. That is what we are going to discuss in this session. Before going to discuss about expectation value, I think you are remembering these things. That is, if a creation operator operates on certain state n, then we get a eigenvalue, that is root n plus 1 get n plus 1. That is, state is changed to n plus 1 from n, and there will be eigenvalue, that is root n plus 1. And if an annihilation operator is operating on state n, then we will get root n get n minus 1. Okay, are you remembering these equations? Please remember. Okay, this is very important. Now we want to find out expectation value of A dagger. That is, this is direct notation, right? And what is this meaning? That is, there is a state n, A dagger get n. This is what represented by this Dirac notation. So we know bra n, and when this creation operator operates on state n, we get a value that is root n plus 1 get n plus 1, right? That is, this is a constant value, so I can take outside. That is, expectation value of a dagger is equal to root n plus 1 into bra n get n plus 1. See, this state is n and this state is n plus 1. These states are not same. That means if you are taking scalar product of two different states, this value will be equal to 0. That is, expectation value of a dagger is equal to 0. Another combination is, and if we are taking a dagger raised to n, see, then also these two states will not be same. So for this combination also it will be equal to 0. Now the second one, that is expectation value of a annihilation operator, that is equal to bra n a get n. So we know when annihilation operates on certain state, you will get bra n, and this value will be root n into get n minus 1. When annihilation operator operates on a state, the state is decreased by 1, right? That is, expectation value of a is equal to, we can take this constant term outside, that is root n bra n get n minus 1. See, these two states are different, so their scalar product will be equal to 0. That is, annihilation operator, expectation value of annihilation operator is equal to 0, and this is true if we take some n times of annihilation operator and its expectation value, that is also equal to 0. The reason is this one only, because the states will be different. If you operated 2 times, then this will be n, and here it will be n minus 2. Okay, that is, if annihilation operator operates on a state, the state will be changed to a lower one, right? Third one, that is expectation value of a dagger plus or minus a. So that is bra n a dagger plus or minus a get n. So we can expand this, that is bra n a dagger get n plus or minus bra n a get n. So when this a dagger operates on n, the state become n plus 1, and when annihilation operator operates on the state become n minus 1. Okay, so when we are considering the scalar product, this will be 0, and the other term also will be 0. Therefore, expectation value of a dagger plus or minus a is also equal to 0. Fourth one, expectation value of a dagger a, that is, this is equal to bra n a dagger a get n. So first this annihilation operator will operates on get n, so we get bra n a dagger. When this operates on get n, we get a root n and get n minus 1. Now this a dagger operator will operates on this one, that is, we can take this root n outside, bra n, and when a dagger operates on this one, we will get a eigenvalue, that is n minus 1 plus 1, that is root n. Get, see, this is increased by 1, that is we get n, that is we got root n into root n bra n get n. This value is equal to 1. Therefore, we got expectation value of a dagger a is equal to n. That is why earlier I told you this is called the number operator. This n is the number of the state, right? That is why it is called number operator. And the fifth one, that is expectation value of a dagger. That is bra n, a dagger, get n. So first this creation operator will operate on get n, and we know if it operates on get n, we get this is equal to root n plus 1 get n plus 1, right? So that is bra n a. Now we got root n plus 1 get n plus 1, right? That is root n plus 1 bra n a get n plus 1. Now this annihilation operator operates on n plus 1. You know, when annihilation operates on n, we get root n get n minus 1, right? So here it is n plus 1. Therefore, that minus 1 will be n. So this is equal to root n plus 1 and bra n, and a dagger operates on this one, you will get root n plus 1, right? Get n. So this is a constant, we can take it outside, that is root n plus 1 into root n plus 1 bra n get n. Here this value is equal to 1, therefore we got a dagger. Expectation value of a dagger is equal to n plus 1. Sixth one, expectation value of a dagger plus a or square. That is bra n, a dagger plus all square means a dagger plus a into a dagger plus a. We can expand this as a square plus 2ab plus b square, because this is not our algebra, this is operator algebra. I already told you the operator algebra is different from algebra. Okay, get n, right? Now this is equal to bra n. We can multiply these terms, that is a dagger, that is a dagger square plus a dagger a plus a dagger plus a get n. See, here also the order is very important. Okay, so we can expand this function, that is equal to bra n, a dagger square get n plus bra n, a dagger a get n plus bra n, a dagger get n plus bra n, a get n. Earlier I told you this one will be definitely equal to 0. We already derived the value, right? If a dagger is operating on the same state, then it will be 0. And I told you this one is nothing but our number operator, so you will get the n value. And earlier we derived this one, that is a dagger is equal to n plus 1. And this one, see, equal to 0. When this annihilation operator operates on this state, then it become, first it become n minus 1, then again this second one will operate, so the state will be n minus 2. Okay, so bra n and get n minus 2 are different, so this is equal to 0. So we got the value, that is equal to expectation value of a dagger plus a all square is equal to 2n plus 1. Seventh one, that is expectation value of a dagger minus a all square. That is equal to bra n, a dagger minus a into a dagger minus a get n. That is, we can expand this one, that is bra n into a dagger square minus a dagger a minus a dagger plus a square get n. And we can expand, that is bra n, a dagger square get n minus bra n, a dagger a get n minus bra n, a dagger get n plus bra n a square n. See, this one will be definitely 0 and this also definitely equal to 0. And here these values we know, that is minus a dagger is n and this is minus n plus 1. Or we can solve it in another way. Earlier we found the value of this term, that is n, the number operator, and the value of this one, that is n plus 1. So we will get expectation value of a dagger minus a all square is equal to minus n plus 1, that is equal to a dagger minus a all square is equal to minus 2n plus 1. Now let us summarize all these ideas. First one, expectation value of annihilation operator a, that is equal to 0. If this is n times, then also this is equal to 0. Second one, creation operator, expectation value of creation operator, and if it is n times also, this is equal to 0. And third one, expectation value of a plus or minus a dagger, that is equal to 0. Fourth one, expectation value of a dagger plus or minus a all square is equal to 2n plus 1, but if it is plus, this will be minus, and if this is minus, this will be plus. And fifth one, expectation value of a dagger plus or minus a all cube is equal to 0, and sixth one, expectation value of a dagger plus or minus a all raised to 4 is equal to 6n square plus 6n plus 3. Here I tell you some trick. If a dagger plus or minus a raised to n is equal to 0 if n value is odd, and this will not be equal to 0 if n is even. See, here this is n is even value, so that is not equal to 0, but here this is odd value, so the value is 0. Here also the value is odd, n is odd, so it is 0. Here n is even, so it is not equal to 0. Okay, so please remember this one. Example problem. First one, find expectation value of a dagger a dagger a. How we can find out? See, this is nothing but bra n a dagger a dagger a, get n. Now this operator will operate on get n. We know if creation operator operate on some state, we will get an eigenvalue root n plus 1 and state n plus 1. If an annihilation operator operates on certain state n, then we will get root n get n minus 1. Okay, this is the rule. So here first this annihilation operator operates on the get n, so we will get bra n a dagger a dagger, and this is root n get n minus 1. Okay, now where we can take this root n outside because it is a constant value, that is root n bra n a dagger a dagger get n minus 1. Now this creation operator will operate on this one, so we will get root n bra n a dagger a, and here it is n minus 1, so root of n minus 1 plus 1, that is n, right, get n. So again we can take it outside, that is we got root n into root n bra n a dagger a get n. So when this annihilation operator operates on this one, so we will get root n bra n a dagger, that is root n into get n minus 1, and we can take this root n outside, that is equal to root n into root n bra n a dagger get n minus 1. So when this a dagger operates on this one, you will get root n root n root n root n minus 1 plus 1 get n minus 1 plus 1, right? Here there is bra n is there, I missed it. Okay, so this is equal to n square into bra n get n. We know this value is equal to 1. So the final answer is equal to n square, right? Another example, expectation value of a dagger, a dagger. So that is bra n a dagger, a dagger get n, right? And we know if creation operator operates on get n, we'll get root n plus 1 get n plus 1, and if annihilation operator operates on state get n, then we'll get root n get n minus 1, right? So now first this creation operator operates, that is bra n a dagger a, and this will be root n plus 1 get n plus 1. Now this annihilation operator will operates, that is bra n a dagger root n plus 1 into, this will be root n plus 1 get n, that is we got n plus 1 outside, then bra n a dagger get n, right? So this will operate again, that is n plus 1 bra n a, when a dagger operates, we will get root n plus 1 get n plus 1, right? Again this will operate on this state get n plus 1, that is n plus 1 root n plus 1 bra n, when this annihilation operates on get n plus 1, we will get an eigenvalue root n plus 1 get n. Okay, that is n plus 1 or square. Okay, an important note: if the question contains expectation value of large number of combination of creation operator and annihilation operator, then how we can solve the problem? The easy method is, we have to check number of a dagger. If number of a dagger is equal to number of a, that is number of creation operator is equal to number of annihilation operator, then the value will be not equal to 0. If the number of creation operator is not equal to number of annihilation operator, then this value definitely will be equal to 0. For this problem, let us check the number of creation operators, that is 1 2 3 4 5 6 7, right? And now we have to check the number of annihilation operator, that is 1 2 3 4 5 6 7 8. See, these numbers are not equal, therefore definitely this value is equal to 0. No need to do any calculation. Now some works for you. Find expectation value of a dagger, a dagger. Find expectation value of a dagger, a, and find expectation value of a dagger, a dagger, a, a dagger. Okay, this is a work for you. Expectation values of x and px. First, we will discuss it for single basis state. Then we will discuss it for linear combination of basis states. So now we are going to discuss about expectation value of x and px for single basis state. We know the expression for creation operator, that is a dagger is equal to 1 by root 2m h cross omega m omega x cap minus I p x cap. And we know annihilation operator, that is a is equal to 1 by root 2m h cross omega m omega x cap plus I p x cap. Here first I am going to add these two operators, that is a dagger plus a, that is equal to 1 by root 2m h cross omega into 2m omega x cap, right? That is equal to, I can simplify this equation because there is root 1 by 2m is there and 2m is there. Okay, so that is root 2m omega by h cross into x cap, right? Therefore, I can write x cap is equal to 1 by or root h cross by 2m omega a dagger plus a. Next I am going to subtract a from a dagger, that is a dagger minus a is equal to 1 by root 2m h cross omega minus 2I p x cap, that is equal to root 2 by m h cross omega, there is a minus I p x cap. So I can write p x cap is equal to I root m h cross omega by 2 into a dagger minus a. So we got two expressions for x cap and px cap in terms of creation and the annihilation operator. That is x cap is equal to root h cross by 2 m omega a dagger plus a, and px cap is equal to I into root h cross by 2 m omega a dagger minus a. Now the first one, we have to find out the expectation value of x cap, that is expectation value of this term, right? That is root of h cross by 2m omega expectation value of a dagger plus a, that is root h cross by 2m omega expectation value of a dagger plus expectation value of a. Here what is this thing? This is bra n a dagger get n. If this creation operator operates on get n, then the state become n plus 1, right? Then the scalar product of these two terms become 0, right? Therefore, expectation value of a dagger for the same state is 0, and for annihilation operator also it is equal to 0. Okay, that is expectation value of x equal to 0 for 1D linear harmonic oscillator. This is quite logical also. See, this is our linear harmonic oscillator potential. Right. This V of x, and this is x equal to 0, and this is plus x, and this is minus x. So the particle is oscillating in this potential. So suppose this is our particle, then it can oscillate. Okay, so the average position of the particle. So the extreme position is minus a, and here the extreme position is plus a. So the average position, I told you expectation value is nothing but average value. So the average value of position of the particle is 0 because there is a minus a and plus a. So when we are taking the average value of the position, we will get expectation value or average value of x equal to 0. Okay. Second one, expectation value of px cap. We know px equal to I into root h cross m omega by 2 into a dagger minus a. So what is expectation value of px? That will be equal to I into root h cross m omega by 2 expectation value of a dagger minus a. That is I into root h cross m omega by 2 expectation value of a dagger minus expectation value of a. Again, these values are equal to 0. So the expectation value of momentum is also equal to 0. This is also logical. Right? This is our potential. V x equal to 0. This is V of x equal to half kx square. Okay, and this is the particle. So the particle can move in this direction, that is positive direction. Okay, so there will be a positive momentum, and it can move in the negative direction, therefore it will have a negative momentum. So when we are taking the average of this momentum, that is px, we will get this is equal to 0. Third one, expectation value of x square, that is equal to, we know x is equal to root of h cross by 2m omega a dagger plus a. Okay, so when we are taking x cap square, that is equal to h cross by 2m omega into a dagger plus a whole square expectation. Okay, that is equal to h cross by 2m omega, and earlier we solved this problem, right? That is, we know this value is equal to 2n plus 1, that is into 2n plus 1. If you are not remembering this value, just solve. Nothing is there. Find expectation value of a dagger plus a into a dagger plus a. Okay, you have to multiply. Okay. Then you have to evaluate. That is very simple thing. Okay, so finally you will get 2n plus 1. Actually, this problem we already solved. That is why I am not doing it here. Okay, so this is the answer. Fourth one, expectation value of p x square, that is equal to, here we know p x is equal to I into root h cross by 2 m omega a dagger minus a. We have to take the square of this term, that is square of I is minus 1 into square of this term is h cross m omega by 2 into expectation value of square of this term, that is a dagger minus a whole square. Actually, we solve for this one also. That is, we got it is equal to minus 2n plus 1. So we can substitute this value here, and finally we will get px cap square is equal to minus 1 into minus. So it will cancel, and finally we will get h cross m omega by 2 into 2n plus 1. Here we are discussing about one-dimensional linear harmonic oscillator. Right. Now I want to find out the uncertainty in position, that is delta x. And also I want to find out uncertainty in momentum also. Okay. First we have to solve the uncertainty in position. That is, there is a particle and it is oscillating in a linear harmonic potential, and we want to find out its position. And I told you, in quantum mechanics, if you are measuring some quantity, there will be some uncertainty, and we want to find out the uncertainty in that measurement. That is what we are going to find out here. That is delta x, uncertainty in the position of the particle if we are trying to measure that. Okay, what is the expression for uncertainty in position? That is root x square minus expectation value of x whole square, right? Here we evaluated both of these values, right? We got this value is equal to 0, expectation value of x, and we know expectation value of x square, that is equal to root of h cross by 2m omega into 2n plus 1. And now I want to find out uncertainty in momentum. If you are measuring the momentum of the particle, so in that measurement there will be some uncertainty, and I want to find out that uncertainty. That is, the expression is expectation value of p square minus expectation value of px square. Here also the expectation value of px is equal to 0. Okay, and we already find out this value, so we'll get root of h cross m omega by 2 into 2n plus 1. So what is the product of uncertainty? Delta x, delta px. This is uncertainty principle, right? That is delta x, delta px. What will be the value of d delta x, delta px? That is, we know delta x is this one. That is root h cross by 2m omega 2n plus 1 into root of h cross m omega by 2 into 2n plus 1. That is, this m omega and m omega will cancel, and the remaining is h cross by 2 into 2n plus 1. And if we are simplifying this expression, then we get delta x, delta px equal to n plus half into h cross, where this n value is equal to 0, 1, 2, etc. That is states. So the lowest uncertainty is for ground state measurement, right? If the particle is in the ground state, then the measurement, if you are measuring the position and momentum of that particle, then uncertainty will be minimum. That is half h cross. If it is in first excited state, then it will be 3 by 2 h cross, right? That is, its uncertainty is more and more as n value increases. Okay. And now let us summarize all these ideas. X cap is equal to root h cross by 2m omega a dagger plus a, and px cap is equal to I into root of h cross m omega by 2 a dagger minus a, and expectation value of x is equal to 0, expectation value of px also equal to 0, expectation value of x square is equal to h cross by 2m omega into 2n plus 1, and the expectation value of px square is equal to h cross m omega by 2 into 2n plus 1, and the uncertainty delta x, delta px is equal to n plus half h cross. Please try to remember all these equations. Okay. In the earlier session, we discussed expectation value of x and px in a single basis state n. Get n. Right. Now, we are going to solve for x and px, average value of x and px in linear combination of basis states, that is psi is equal to a psi n plus b psi n plus 1, where n and n plus 1 are successive states. Okay, so now this is our wave function. Okay, there is two states, one is psi n and other is psi n plus 1. And the state of the particle is linear combination of these two. And here we are going to find out expectation value of x, expectation value of px, then the time evolution, that is expectation value of x after some time t, and expectation value of px after some time t, and expectation value of x square, expectation value of px square, and their time evolution also. Okay, this is the overview of what we are going to discuss. That is, now the particle is in a state psi, which is the linear combination of two states, that is a psi n plus b psi n plus 1. In Dirac notation, we can write this as ket psi is equal to a ket n plus b ket n plus 1. Now, first we are going to evaluate expectation value of x. That is, we know expectation value of x is equal to bra psi x cap ket psi. Here, now this is our state. That is equal to, we have to take the complex conjugate of ket psi, then we will get bra psi, right? That is a star bra n plus b star bra n plus 1 into x cap into a ket n plus b ket n plus 1. That is equal to a star a bra n x cap ket n plus a star b bra n x cap ket n plus 1 plus b star a bra n plus 1 x cap ket 1 plus b star b bra n plus 1 x cap ket n plus 1. See, this is nothing but modulus of a square, and this is nothing but modulus of b square. And we know the expectation value of x, this is nothing but expectation value of x is equal to 0 for 1D linear harmonic oscillator, and this one is also expectation value, that is also should be equal to 0, because this is a linear harmonic oscillator, symmetric linear harmonic oscillator. Okay, so the remaining term is a star b bra n x cap n plus 1 plus b star a bra n plus 1 x cap ket n. Here we know the x cap operator in terms of creation and the annihilation operator, that is root h cross by 2m omega a dagger plus a. That is, we have to substitute this value, that is we get root h cross by 2m omega as a common term into a star b bra n a dagger plus a ket n plus 1 plus b star a bra n plus 1 x cap is a dagger plus a ket n. So here what we have, bra n. Okay, so if this annihilation operator operates on the state, we will get n. Okay, and if this one operates on this one, then we will get a state n plus 1. So here the combination of these two, scalar product of these two is equal to 0 and this one is equal to 1, right? And when this annihilation operates on get n, we get a state that is n minus 1. And the scalar product of these two is equal to 0. Okay, because these states are different. And if we take a dagger on the state, then we will get a state get n plus 1. So these two states, when taking the scalar product of these two states, we get this is equal to 1. Okay, therefore we get this is equal to root h cross by 2m omega a dagger b. Here this operator, that is annihilation operator, give a eigenvalue that is root n plus 1, right, plus b star a, and here this operator, that is creation operator, gives an eigenvalue root n plus 1. Okay, that is we got this is equal to root h cross by 2m omega into root n plus 1 into a star b plus b star a. That is we got expectation value of x is equal to root of h cross by 2m omega root n plus 1 a star b plus b star a. Now example problems. This state is a linear combination of two states, that is psi is equal to 1 by root 2 psi 1 plus I by root 2 psi 2. That is here a is equal to 1 by root 2 and b is equal to I by root 2 and n value. See, here we need a n value. The n value is the lowest state. That is here n is 1 and 2 are there. So the lowest state is n equal to 1. And we want to find out a star and b star, that is conjugate of a and b. That is a star is equal to 1 by root 2 and b star is equal to, here there is I. So when we are taking the conjugate, it become minus I by root 2. Now we have to substitute these values in the expression, that is expectation value of x is equal to root of h cross by 2m omega root n plus 1, that is n equal to 1, that is n plus 1 is 2 into a star is 1 by root 2 into b, that is I by root 2 plus b star is minus I by root 2 into a is 1 by root 2. That is we got this is equal to root h cross by m omega into this is I by 2 minus I by 2. That is expectation value of x is equal to 0. Another example, psi is equal to root 2 by 3 psi 0 plus 1 by root 3 psi 1. Here also the question is to find out expectation value of x. We know the expectation value of x is equal to root h cross by 2m omega root n plus 1 into a star b plus b star a, right? So we have to find out these values, that is a is equal to root 2 by 3, b is equal to 1 by root 3 and n is the lowest state, that is n equal to 0. And we have to find out a star and b star, that is a star is equal to root 2 by 3, b star is also equal to 1 by root 3. If there is some I terms, then it become minus I. But here both are real values, so the conjugate value is also same as the above. Now we have to substitute all these values in the expression, that is x cap is equal to root h cross by 2m omega into root n plus 1, that is root 1 a star. A star is root 2 by 3 into b, that is 1 by root 3 plus b star is 1 by root 3 into a is root 2 by 3. That is, we got this is equal to root h cross by 2m omega into root 2 by 3 plus root 2 by 3. That is equal to 2 by 3 root h cross by m omega. Example 3. The wave function psi is equal to 3 psi 1 plus 4i psi 2. Find expectation value of x. Here also we know what is expectation value of x, that is equal to root h cross by 2m omega root n plus 1 into a star b plus b star a. Now we have to find out the a value, that is 3, b value, that is 4i, and n is equal to 1, and a star is equal to 3 and b star is equal to minus 4i. Now we have to substitute all these values in the above expression, that is x is equal to root of h cross by 2m omega root n plus 1, that is root 2 into a star b, that is 3 into 4i plus b star, that is minus 4i into a, that is 3. Okay, that is this is equal to 0. So expectation value of x for the state is equal to 0. Here see, one of the coefficient contain I terms, and the first example also one of the term contain I term. If any one coefficient is imaginary, this is a linear combination of two states, right? So any one of the coefficient is imaginary, then the expectation value x will be equal to 0. This is always true. So if you know this trick, some problem you can solve very easily. Now let us consider expectation value of Px. That is, there is a state, that is psi equal to a psi n plus b psi n plus 1. In Dirac notation, get psi is equal to a get n plus b get n plus 1. Now we have to evaluate Px cap. Expectation value of Px cap, that is bra psi Px cap get psi. That is, we have to take conjugate of this get psi. So we will get bra psi, that is equal to a star bra n plus b star bra n plus 1. Okay, so we can substitute all these values here. That is, we get a star bra n plus b star bra n plus 1 into p x cap into get psi, that is a get n plus b get n plus 1. So we will get this is equal to a star a bra n p x cap get n plus a star b bra n p x cap get n plus 1 plus B star A bra n plus 1 P x cap get n plus B star B bra n plus 1 P x cap get n plus 1. Here also see this is expectation value of Px that we know this is equal to 0. It is in the same state nn. Okay, so that value will be equal to 0. And here also expectation value of Px, and these are the same states. So this also equal to 0. So there is only two remaining terms, that is expectation value of Px is equal to A star B bra n P x cap get n plus 1 plus B star A bra n plus 1 P x cap get n. Now we have to substitute for Px cap. What is Px cap? That is equal to I root h cross m omega by 2 into A dagger minus A. That is, we will get this is equal to expectation value of Px is equal to I. We can take this is common as a common term, that is root of h cross m omega by 2 into A star B bra n get Px cap, that is A dagger minus A into n plus 1 plus B star A bra n plus 1 Px cap is A dagger minus A get n. So if A operates on this state, that state become get n, right? So this n and n will give a value that is equal to 1. And if A dagger is operated on this one, then the state become n plus 2, right? And when we are taking the scalar product of these two states, this is equal to 0. Okay, so similarly here also. So we will get P x cap is equal to I root h cross m omega by 2 A star B. Here this one will give the value, that is minus is there into bra n A n plus 1 get n plus 1 plus this is into, right, plus B star A, and here this is n plus 1. So when A dagger operates on this one, this become get n plus 1, and that will give a value 1. Okay, that is bra n plus 1 A dagger get n. That is, we got this is equal to I root h cross m omega by 2 into minus A star B, and when this annihilation operator operates on this one, we will get a value that is root n plus 1 get n, right? So this is root n plus 1, and this get n and bra n will give value 1. Okay, so this is the value plus B star A, and when this A dagger operates on this one, you will get a value root n plus 1 get n plus 1. Okay, that is root n plus 1. That is, we got expectation value of Px is equal to I root h cross m omega by 2 root n plus 1 into B star A minus A star B. That is, we got expectation value of Px is equal to I into root h cross m omega by 2 root n plus 1 into B star A minus A star B. Now let us consider an example problem. That is, state psi is equal to 1 by root 2 psi 1 plus I by root 2 psi 2. That is, here A is equal to 1 by root 2 and B is equal to I by root 2 and n value is equal to, see, we need n value, right? So n value is equal to the lowest state, that is 1. And we have to evaluate this B star and A star, that is A star is equal to, this is a real value, so that one is okay, and B star, here there is I time, so that become minus I by root 2. Now we have to substitute all this value in this expression, that is Px equal to I into root of h cross m omega by 2 root n plus 1, that is 1 plus 1 2 into B star. What is B star? B star is minus I by root 2 into A, that is 1 by root 2 minus A star. A star is 1 by root 2 into B, that is I by root 2. So we got this is equal to I root of h cross m omega. So we can cancel this root 2 and root 2, right? Remaining is minus I by 2 minus I by 2. That is I into root h cross m omega into minus I, right? That is equal to minus I into I, that is plus 1. So the final answer is root h cross m omega. Here you please note, here one of the coefficient is I, complex one, right? So we got a value for expectation value of Px. Now let us check another example problem. Next example, psi is equal to root 2 by 3 psi 0 plus 1 by root 3 psi 1. And the question is to find out expectation value of Px, and we know expectation value of Px is equal to I root h cross m omega by 2 root n plus 1 into B star A minus A star B. Okay, so first you have to find out n and the coefficient A and B, right? So what is A? A is equal to root 2 by 3, and what is B? That is equal to 1 by root 3, and what is n? N is the lowest value, that is 0. And we have to find out the star conjugate values, that is A star is equal to, this is a real value, so 2 by 3, and B star is also equal to 1 by root 3. Now we have to substitute all these values in this expression, that is expectation value of Px is equal to I root h cross m omega by 2 root n plus 1, that is 1, right, into B star, that is 1 by root 3 into A, that is root 2 by 3 minus the same times, right, A star is root 2 by 3 into B is 1 by root 3. So these two terms will cancel each other. Okay, so we will get Px is equal to 0. Here see, both the coefficients are real. And finally, we got the expectation value is equal to 0. You just please note this fact. Okay, we will make some conclusion based on these facts. One more example problem. That is psi is equal to 3 psi 1 plus 4I psi 2. Here also the question is to find out expectation value of Px. That is, we know Px is equal to I root h cross m omega by 2 root n plus 1 into B star A minus A star B. Okay, so we have to find out A value, that is 3, and B value, that is 4I, and N value is equal to 1. And we can find out A star, that is 3, and B star, that is minus 4I. Now we have to substitute all these values in this expression, that is expectation value of x that is equal to I root h cross m omega by 2 root n plus 1, that is n is 1, so it is 2 into b star, that is minus 4i into a, that is 3 minus a star. A star is 3 into b, that is 4i. So we got this is equal to this root 2 and root 2 will cancel, and I root h cross m omega into this is 2 into minus 12i, right? And this will be equal to, there is minus I and I, so it will be plus, so 24 root h cross m omega. Another example problem, that is psi is equal to 3 psi 1 plus 4i psi 2. Here also the question is to find out px, expectation value of px. Here this wave function is not normalized. See, if you are taking the square of coefficient, that is mod 3 square plus mod 4i square, it is not equal to 1. That is why I am telling this is not a normalized wave function. So before solving this problem, we have to normalize. Then only it can represent the real physical situation. How we can normalize? That is bra psi, get psi should be equal to 1. So in order to normalize, we have to evaluate mod 3 square plus mod 4i square. That is 9 plus 16, that is 25. So if you are modifying this wave function as 1 by root 25, psi 1 by root 25, psi, then you will get a value is equal to 1. Okay, so this is the normalized wave function. Therefore, the normalized wave function psi will be equal to 3 by 5 psi 1 plus 4i by 5 psi 2. Now the question is to find out expectation value of px, right? And we know the expression for px. Expectation value of px is equal to I root h cross m omega by 2 root n plus 1 b star a minus a star b. And we have to find out the values of a, that is 3 by 5, b, that is 4i by 5, and we have to find out its conjugate, that is a star is 3 by 5 and b star is minus 4i by 5, and n value is equal to 1. Now we can substitute all these values, that is expectation value of px is equal to I root h cross m omega by 2 root n plus 1, that is 2, and b star, that is minus 4i by 5 into a, that is 3 by 5 minus a star, that is 3 by 5 into b, that is 4i by 5. On evaluating this value, we will get px is equal to 24 by 25 root h cross m omega. So here also we got expectation value for px, and here you see one of the coefficient contains a complex type item, right? That is, we can make a note. If one of the coefficients is imaginary, that is, we are discussing about linear combination of states. So if one of the coefficient is imaginary, then expectation value of px will be not equal to 0. And if all coefficients are real, then we can definitely say expectation value of Px will be equal to 0. Now let us summarize those ideas. That is, here we are discussing about linear combination of states, that is psi is equal to A psi 1 plus B psi 2, where A and B are the coefficients after normalization. Okay, and we got expectation value of x is equal to root h cross by 2m omega root n plus 1 into a star b plus b star a. And I told you one important note, that is, if any one of the coefficient means a, b, right? And if any one of this coefficient is imaginary, then the expectation value of x will be equal to 0. And if it is not imaginary, then you will get a value. Okay, and the second one, expectation value of Px, that is I root h cross m omega by 2 root n plus 1 b star a minus a star b. And I told you an important note also, that is, if any one of coefficient is imaginary, then the expectation value of Px will not be equal to 0. And if all are real constants, coefficients, then the expectation value of Px definitely will be equal to 0. Here we are discussing about linear combination of states. And we are find out the expectation value of x and the expectation value of Px for a linear combination of state, that is psi is equal to a psi 1 plus b psi 2. Okay, now in the next step I am going to find out expectation value of x at time t and expectation value of Px at the time t. So this is about time evolution. Thus, I want to know what will happen to the expectation value of position of this linear harmonic oscillator after time t, and what will happen to the expectation value of momentum of this linear harmonic oscillator after some time t. That is what we are going to solve. And in the earlier session, we discussed about expectation value of x and the expectation value of Px at a time t equal to 0. And I told you the idea of time evolution, that is, if there is a wave function, that is psi of x0, and if you want to find out the wave function at certain time t, then, and if it is psi 1, right? And then how you can find out this wave function at certain time t? The method is you have to multiply it with the e raised to minus I e1 t by h cross, okay, psi of x0. That is, this one is, E1 is the energy of state psi 1. Okay, so if you multiply the wave function at time t equal to 0 by this factor, then you can find out the wave function at time t. Okay, this is the idea of time evolution. Now we are going to use this expression. Okay, so please remember. Let us consider a state at time t equal to 0, that is a psi n plus b psi n plus 1. This is at time t equal to 0. Now I want to find out the time evolution, that is this wave function at time t. So I told you the method, that is time evolution. We derived this expression from Schrodinger equation, right? And the time evolution is psi n xt is equal to e raised to minus I e n t by h cross into psi n of x0. Okay. So we can write this as a into e raised to minus I. Here the energy associated with state is n t by h cross into psi n plus b e raised to minus I e n plus 1 t by h cross into psi n plus 1. Similarly, we can find out this conjugate, that is psi t star, that is equal to a star e raised to I e n t by h cross psi n, that is bra psi n, that is psi n star, plus b star e raised to I e n plus 1 t by h cross psi n plus 1. Now we have to find out the expectation value of x, that is at time t, right? That is bra psi t x get psi t. This is what we have to evaluate. This one is the get psi t, right? And this one is bra psi t. That is star is generally representing the bra and the other one is generally representing the get. Okay. So we have to substitute this terms here. That is we get bra psi t is equal to a star e raised to I e n t by h cross psi n star plus b star e raised to I e n plus 1 t by h cross into psi n plus 1 into x cap into get psi t, right? That is a e raised to minus I e n t by h cross psi n plus b e raised to minus I e n plus 1 t by h cross psi n plus 1. So we can take the multiplication, that is expectation value of x at time t is equal to a star a, and here e raised to I e n t by h cross is there, and here there is e raised to minus I e n t by h cross. So when we are multiplying these two terms, we will get 1, right? And bra n x cap get n. I am representing psi n star as bra n. Okay. Plus, now we have to take the other combination, that is this one and this type, right? So we will get a star b e raised to I e n t by h cross into e raised to minus I e n plus 1 t by h cross bra n x cap get n plus 1 plus, now we have to take this combination, that is b star a e raised to I e n plus 1 t by h cross into e raised to minus I e n t by h cross. I am representing as n plus 1 x cap get n plus the last type, that is this 2, that is b star a e raised to minus I e n plus 1 t by h cross e raised to minus I E n plus 1 t by h cross. Sorry, here it is plus, right? Bra n plus 1 x cap ket n plus 1. Okay, here this one is equal to 1. When we are multiplying this 2, we get a 1. And now we have to substitute this x cap operator, that is equal to root h cross by 2m omega into a dagger plus a. Okay, so we have to substitute this x cap for these terms and we have to evaluate. So here you see this is expectation value of x. These are the same states. So we know this value, that is equal to 0. And here also expectation value of x in the same state is equal to 0. So x cap at time t is reduces to a star b, and here we can multiply this term, so we will get e raised to minus I e n minus e n plus 1 into t by h cross, and this is bra n x cap, and I can take this constant term also outside, that is root of h cross 2 m omega bra n x cap, the remaining term is a dagger plus a ket n plus 1 plus this term, that is b star a e raised to I into e n plus 1 minus e n t by h cross root h cross by 2m omega bra n plus 1 a dagger plus a ket n. Here what is this value of e n minus e n plus 1? See, we know for 1D LHO, the energy expression En is equal to n plus half h cross omega, and En plus 1 is equal to n plus 3 by 2 h cross omega. And what is the difference between these two? That is h cross omega, right? That is En plus 1 minus En is equal to h cross omega. Okay, so we will get this is equal to h cross omega, right? That is expectation value of x at time t is equal to a star b e raised to, here there is a minus I, so I am taking that minus term inside, so I will get I into h cross omega by h cross, so only omega t, and root h cross by 2m omega. See, this is bra n and a dagger plus a. If annihilation operator operates on this one, we will get a get n. Okay, so this get n and this will give the value 1 and the other term is vanishes. So we will get this is equal to root n plus 1 plus the second term, that is b star a into e raised to I omega t into root h cross by 2m omega. Here when a dagger operates on this one, we will get root n plus 1 get n plus 1. Okay, so this will give value 1 and other term will give 0. Okay, that is we will get root n plus 1. So we can simplify this term, that is expectation value of x at time t is equal to root of h cross by 2m omega root n plus 1 into a star b e raised to minus I omega t plus b star a e raised to I omega t. in the derivation I made a small mistake, that is this one is plus, so here we will get minus I. Okay, so this is the final result. Expectation value of x at time t is equal to root h cross by 2 m omega root n plus 1 into a star b e raised to minus I omega t plus b star a e raised to I omega t. In a similar fashion, you please try to solve for px at time t. This is a work for you. The final answer I will tell you, that is expectation value of px at time t will be equal to I root h cross m omega by 2 root n plus 1 into minus a star b e raised to minus I omega t plus b star a e raised to I omega t. This will be the final answer. So you please try to solve expectation value of px at t in a similar fashion we solve for expectation value of x. Here I tell you a trick to find out this expectation value of px if we know expectation value of x. That is, we know d by dt of expectation value of x is equal to expectation value of p by m. This is from Ehrenfest theorem, right? So the expectation value of p can be written as m into d by dt of expectation value of x. Here we already find the expectation value of x in terms of time. So we can find out the expectation value of momentum at time t. That is, expectation value of p at time t is equal to m into d by dt of expectation value of x, that is root of h cross by 2 m omega root n plus 1 into a star b e raised to minus I omega t plus b star a e raised to I omega t. Now just solve this derivative, that is m into, we can take this constants outside, that is root h cross by 2 m omega root n plus 1, and now we have to take the derivative, that is a star b, and derivative of exponential function is minus I omega t into minus I omega plus b star a, derivative of exponential function is I omega t into I omega. That is, expectation value of p at time t is equal to, here we can take this I omega as common term, and here there is one m, so this m and this m will cancels, so we will get I into root h cross m omega by 2 root n plus 1 minus a star b e raised to minus I omega t plus b star a e raised to I omega t. See, this is the solution we earlier obtained. So if you know the expectation value of x, then no need to do all the derivation, you just use this Ehrenfest theorem. Then you can easily find out the momentum at time t. Now let us discuss expectation value of x square. In two cases, one is at t equal to 0 and we will discuss at time t also. Okay, we know the x cap operator is equal to root h cross by 2m omega into a dagger plus a. So what will be x cap square? That will be equal to h cross by 2m omega into a dagger plus a into a dagger plus a. That is, x cap square is equal to h cross by 2m omega a dagger square plus a dagger a plus a dagger plus a square. Now let us consider our linear combination of states, that is psi is equal to a psi n plus b psi n plus 1. Now we have to find out this expectation value of x square in this state, that is x square is equal to bra psi x cap square get psi, that is equal to bra a star psi n star plus b star psi n plus 1 x cap square get a psi n plus b psi n plus 1. That is, when we are expanding this term, we will get this is equal to a star a bra n x cap square get n plus a star b bra n x cap square get n plus 1 plus b star a bra n plus 1 x cap square get n plus b star b n plus 1 x cap square get n plus 1. Now you have to check the x cap square. Here this is expectation value of x cap square, and these are all our expectation value with the same state or different states. And now you have to cross check with this x cap square value. So you can identify the combination of states for which the expectation value will vanish. That is, for this one, this expectation value will vanish, and also for this one, the expectation value will vanish. The reason is, here this a dagger square, so the state will be increased by 2. Here the state is same. Here also the final state will be same. Here the state is reduced by 2. Okay, that is the key idea. So by using those ideas, you can check which of the expectation values will vanish. So here these two will vanish. So we got expectation value of x square is equal to mod a square, expectation value of x square in the state n plus mod b square, expectation value of x square in the state n plus 1. And if you try to evaluate the time evolution, that is x cap square at time t, then also you will get the same answer. Okay, now we have to evaluate expectation value of p x cap square. In the state psi is equal to linear combination of two states, that is a psi n plus b psi n plus 1. You please try to solve as we done earlier. So finally you will get this value, that is p x cap square is equal to mod a square p x cap square in the state n, that is expectation value of p x square in the state n plus mod b square expectation value of p x cap square in the state n plus 1. Now let us summarize these ideas. That is, we are considered a linear combination of states, that is psi is equal to a psi 1 psi n plus b psi n plus 1. And we found expectation value of x at time t is equal to root of h cross by 2m omega root n plus 1 into a star b e raised to minus I omega t plus b star a e raised to I omega t. And we got expectation value of px at time t, and I told you we can use Ehrenfest's theorem to solve this in a tricky way. That is equal to m d by dt of expectation value of x, that is equal to I into, we got root h cross m omega by 2 root n plus 1 into minus a star b e raised to minus I omega t plus b star a e raised to I omega t. And we got expectation value of x square at time t equal to 0, that is equal to mod a square expectation value of x square in the state n plus mod b square expectation value of x square in the state n plus 1. And if you are evaluate these two values, then this is equal to h cross by 2m omega into mod a square into 2n plus 1 plus mod b square into 2n plus 3. And expectation value of p x square at a time t equal to 0. And I told you this value will be same for expectation value of x square at a time also. Okay. Now the expectation value of px square at time t equal to 0, and I told you this is equal to expectation value of p x square at time t also. Okay, and that is equal to, we got mod a square expectation value of p square in the state n plus mod b square expectation value of p square in the state n plus 1. And if you find out these terms, then you can write this is equal to h cross m omega by 2 into mod a square into 2n plus 1 plus mod b square into 2n plus